Alright, very good morning, very good afternoon to all of the esteemed guests, my dear friends and my fellow presenters here. My name is Shomenik Bharti and I'm here to present our paper number 64, a glass policy, a quantum-inspired RL framework for brittle mastery and upskilling. I represent System Unity University and the other co-authors as well, whose names you can see on the screen currently. And I'll move forward as we have some time constraints as I have been told. So, to introduce the problem statement, a lot of the startups or a lot of companies in fact require a huge amounts of data sets to train employees, especially when we look at larger startups or mid-tier startups. They require lots and lots of data sets and like in petabytes to historical data sets to train employees in the future as well. So I mean that's a huge problem considering a lot of up-and-coming startups, the smaller startups or like the 1 or 2 year startups don't have access to such data sets. I mean this is a huge problem statement. And the second problem, apart from the cold start problem as I just mentioned, is also the fact that they often have a strict budget limitations, right? It could be in any type of units or any type of currency, but ultimately there is a budget limitation as well as a time limitation. So we have already recognized 3 limitations. Number 1, budget. Number 2, time. And number 3 is the ultimate cold start or the lack of historical dataset problem. So we have created a customized framework for personalized training through quantum reinforcement learning. And we have proposed the framework as QAbacus or Quantum Adaptive Budget Aware Cold Start Upskilling System. So it's a budget constrained reinforcement learning system. We have used budget constrained MDP or like a Markov decision processor. Essentially what it does is it's a Markov decision process, but it's strictly limited by its budget, and any type of stochastic, training, after the training, if we discover any type of agent has surpassed the budget, we treat it as a complete failure. So that is how we have framed the whole problem statement as. Now I would like to focus on the literature review or what algorithms exist in this specific domain. So as I mentioned, the first problem was that a lot of the startups take or train employees based on gut feeling, or there is no standardized algorithm existing to do the same. So I mean there are a few algorithms as you can see here. RL major is a very common one. The major problem in this case is there's a requirement of huge amounts of data sets, and especially like the data sets that are present are very much personalized or general. So when we require data sets that are specialized, that's a huge lacking in this current domain. So our problem statement is essentially the objective of the entire QAbacus framework is to maximize employee skill improvement under strict budget limits. Now, how do we frame employee skill requirements? So we have designed 8 skill vectors in different areas such as coding, English, it could be anything else, and that is part of the client or whoever wants to use the framework essentially. And we have trained thousands and thousands of simulated agents in simulated environments, and we have tried to complete each agent's training course in the minimum budget possible and try to basically create a system which can propose which next training course to take based on the current state and other available budget, right? So as you can see, the flowchart is very self-explanatory. The past record problem, the strict budget problem, and the uncertainty problem is very much evident in this flowchart. Now, what is a novelty? I mean, this is a huge, I would say, a big question, right? The first thing that I need to make clear is the fact that this is a classical problem statement which is inspired from quantum machine learning. The way it works is we have used a bond rule probability selection method, which essentially means the probability of selecting the next action not only depends on the softmax function which is normally used. We have used basically what we've used is a wave function, and we have assumed that the probability of the next action is directly proportional to the square of the wave function, which is obviously bond rule. So we have assumed that, and then we have made the algorithm based upon that. So what's the advantage of this? That's the biggest question I feel like. The main advantage of this is it allows the agent to select multiple states all at once and then explore the best one instead of collapsing into a single state right from the get-go. So for example, if a employee is learning to code first, and then the next stage could be, I don't know, like learning English or something.
How to select the phase?
So that is what the algorithm does. That is a reinforcement learning problem. We have framed it as an actor-critic method. So the actor makes the choice. Yeah, sure. So this is the proposed method. I'll be very quick. So we've used an actor-critic method. The actor proposes or selects a certain choice based on the probabilistic simulations that we have run using the Bond rule and the von Neumann entropy. The von Neumann entropy is nothing but it states that the higher the entropy is, basically the more abrupt the agent is at making decisions, the lower the entropy, the better. That is, it's making a deterministic choice essentially. I mean, after that, we've used a critic, which is basically criticizing the decision. It's almost like a GAN simulation, as you might have understood. And I'd just like to cover one more very important. Yes, sir. Yeah, I would like to cover one more very important component of this whole framework. Is we've introduced a new metric, and the metric is one second. Policy decoherence. What is policy decoherence? Policy decoherence measures the amount that a certain agent has deviated from its given task to the next probable task, and that is what policy decoherence is. I would like to move on to the result section. The reason is evident. Okay, so in the result section, as you might have seen, sir, the red dotted line that you see is the budget. It's the 100% budget that you see. The blue lines you see is in the deterministic environment of the case 1 environment. So in the first case, we have trained the RL environment. It's very successful at utilizing the full budget, like the budget up to its maximum, and then like stay within the budget, so it hugs the budget and moves forward. However, when we move at the stochastic environment, where we have introduced some Gaussian noise and some other environmental factors, we see that there's there's stochastic overshoots, which means that whenever we introduce stochasticity in the whole process, the system basically breaks. In fact, that is the reason why we named it as glass policy. That is, it's brittle, but it's also very transparent. Yeah, so ROI is a metric that we have used. There are, I've added here, we have used 5 primary metrics, as you can see. That's success rate, budget violation rate, ROI, conversion speed, and policy entropy. Return of investment. Return of investment or ROI. It's a general term that we mentioned. And like finally, as you can see, sir, we had trained 4 or 5 different methods, and our method is the one that converges rapidly. It's the Abacus proposed method. The other ones include frugal, high, it includes the terminal focused, balanced, and then the insensitivized method. Just like to conclude the whole process, the algorithm works in this way. Essentially, the decision can be either to take a new action or to wait. Like wait and see kind of a thing. So the yellow spots that you see on the sideways, the graph here is the wait action. So we have visualized the entire decision making process. The reason to show this here, right here, was to show that the entire process is very transparent, but also to show that under stochastic environment it very much breaks. That is a big problem statement that is like going to be a big work down the line. So yeah, and yeah, this is pretty much it.
Alright, I understand, but
sure.
Just tell me,
yeah.
Where is the field of application?
Okay, so as I mentioned, sir, a lot of the new startups that are up and coming. For example, I'll just give an example, sir. You've created a Netflix account, right? 5 seconds ago. Now, how does Netflix know what movies to recommend to you? It does not have any historical data set based on you. It does have a lot of historical data sets based on the other users. But when we imagine a startup, it doesn't even have that. When we imagine a startup and it wants to train XYZ amount of employees, it doesn't have the historical data that's required to train the new employees. So for example, when we want to go to a full employee training course, what action to take is simply based on a regular course that's same and general for every employee out there.
Why do you take the center of reinforcement learning?
So the ultimate reason is that there are 2 components to this question. The first question is why reinforcement learning, and the second one is why quantum inspired reinforcement learning. Reinforcement learning was used to simulate the environment where the employee training takes place. This wouldn't have been possible without a Markov decision process. So essentially, it's a sequential learning process. Like the agent learns one specific skill, it improves that, and then it tries to improve another skill. So it's a sequential process instead of the regular, typical, I would say, environments. It's not possible in a non-reinforcement learning environment. And the second question is why quantum. There is no data set. That's the main thing. The entire algorithm works without any type of historical data set. That is a key component, as I mentioned. I didn't have the time enough to show this actually, but if I'm allowed to, in the data set, because we've clearly written no real data set has been used. We have actually simulated a data set.
Data set you have?
No, there is no data set actually.
Simulated data set you have?
No. Because the environment has simulated essentially rules. So, for example, the budget can't be broken. Yes. Yeah, I mean, you can consider that. Yes, definitely. So, for example, there are traffic rules, but then we don't have the data set, specific data set for a specific employee. So, A, it's very transparent, it's explainable, and B, it's customizable to each training program or each person or individual or whatever you want, and 3, it doesn't require any type of historical data set. Yeah.
Let me ask you a basic question.
Sure.
What is supervised learning?
So supervised learning is a technique where we use data set like labels and like x and y both are present, and we give it to the algorithm and it predicts a certain value. So it learns the mapping from x to the y, and then it tries to predict it on unknown values where the y is not known, and that is what.
Supervised learning?
Unsupervised learning is a learning technique without any data set.
Reinforcement learning?
Reinforcement learning is a type of learning where we take the agent works in a specific simulated environment and it learns basically through sequentially, it learns the best, I would say, choices based on the current given action. We use MVP, which means sequentially we learn through every step. Especially if you look to the future step as it's like next decision making, I would say, algorithm. That is how it works. We can just use our example actually. It's a constrained Markov decision process. That is a very good example. We can also state actor-critic method, which the actor takes the decision and the critic criticizes the decision. Compare a teacher and a student learning. So teacher teaches some
self-driving.
Yeah, sure. Self-driving. I mean, as a real life example, it's a great example. Sure. Self-driving or like anything else. Reinforcement is
How
not.
do you transform these rules or norm or your predicate code to quantum code?
So
My point is very point.
Yeah.
Question is point.
Yeah.
That you are saying this is not my data set.
Mhm.
Set of norm rule. How do you fit it in quantum domain?
Because, sir, consider this. There's a reinforcement learning algorithm. Normally, it uses softmax algorithm. Softmax as the activation function, right? We propose that instead of using softmax, let's use the bond rule probability function. So essentially, it's quantum-inspired machine learning. It's a classical machine learning, but the probability system or the entire class-based system is replaced by a quantum-based system. So, if an agent decides to learn coding as its next step, it instead of committing fully to a certain route, it will consider all of the given probabilities given the current scenario, and it will consider the best one. So essentially, instead of softmax, so for example, 0.8, 0.1, 0.1.
You compare it with classical.
Classical machine learning, it's not possible. Classical reinforcement learning, because it's a sequential
How
process.
you compare that?
Yeah, sure. Because we've used classical reinforcement learning, not machine learning. So this one is the classical. The red one. The orange one, actually.
Orange one?
The classical reinforcement learning algorithm. The blue one is ours. The rapid convergence one. It trains in very small number of
What is
boxes.
the topmost one?
The red one, it overshoots, as you can see.
Going and flat.
Sorry, which one, sir?
Going and flat.
Yeah, because there's a budget, so it sticks to that budget. It cannot overshoot beyond that. So, for example, if I have 100 rupees, I can't spend beyond. If I spend beyond that, that's like overshooting, and that's not ideal for our case. We are trying to gain the maximum number of skills in a short amount of given time, given a short amount of budget, essentially, using a quantum-inspired reinforcement learning framework. That's the entire end-to-end framework.
Anybody has any point to ask?
You don't have any data sets, so how we can plot this one?
Because essentially we are using this plot is nothing but a ROI plot. So it's like
If you don't have any data,
Sure.
how we can plot?
why? Because we can calculate based on the current scenario. Based on the current. So, for example, if I say that in a reinforcement learning scenario, the data set is simulated. So essentially, imagine a rule-based environment. So there are certain rules in the environment that the agent must follow. That is how reinforcement learning works. In our case, we don't have any historical data set, but there are the rules. If there is a breaking of any rule, we penalize the agent or whatever. And we are also measuring metrics at each step. So your question ultimately boils down to how are we measuring metrics? in each step. Actually, we have proposed 5 different metrics. As you saw here, the metrics are the 5 different things. The success rate, which is easily measurable. If it sticks beyond the budget while hugging the budget and moves forward in the given space, essentially, that is a high success situation. We don't need a historical data set to prove that our algorithm is the kind of the best out of all the given algorithms, essentially. And the ROI is the same thing, and the conversion speed is the same thing. The policy entropy just dictates that the von Neumann entropy. So it's essentially the lower it is, the better it is. So I mean, that's how we frame the whole problem.
Anybody has any point?
Have you published this?
Yes.
Where do you publish it? Where do you publish it?
Published as in.
Full
No, it's not. It's actually being processed into a journal with a lot of Professor Povich is also working on this with us. It's a lot of professors. Povich sir. Yes, I have also worked at IIT. This was actually done in the HPC supercomputer cluster for India. So yeah.
So, thank you, Shomodhi. May we have the certificate?